Hello and welcome to your chemistry lecture. It's Professor Dowd, and we're doing something a little different this week. So all of this chapter on the gas laws is going to be condensed into one lecture for reasons that you'll see. Basically, there's not really a good place to split this stuff up because they're all very closely related. And the other thing we're going to do is the gas laws themselves kind of tell a really interesting story about the history of science. And I wanted to try to share that in a lecture with you to hopefully make it more interesting. And the more you understand about how we know these things, I feel like the more you'll understand how science is made or how science is done, both the history of it, and then you can imagine the same things going on today. But first off, we want to note that in this chapter, we're talking about gases. And gases have certain characteristics or certain ways to measure them that we're already familiar with, but we want to make sure that we kind of spell it out here to fully understand what we're talking about. So starting from volume, of course, the volume of a gas is the amount of space that it occupies, and a gas always fills its container. So whatever the shape of the container, whatever the size of the container, any gas that's inside will occupy the volume of that container. Note that for gases, usually it's going to be measured in liters, although you could also measure it in milliliters. And yeah, we'll talk more about this here in a little bit. Temperature, let's review what we know about temperature. Remember that the temperature of a gas is going to relate to the average kinetic energy of the molecules in a substance when it's measured in Kelvin. So in other words, when you increase the Kelvin temperature of a substance, the speed at which the molecules are moving they move faster. Likewise, when you decrease the temperature, molecules move slower, and therefore they have fewer collisions. Keep in mind with a gas that, with a liquid, for example, or a solid, we have our particles in constant contact with one another. That's not the case with a gas. They're far apart. And so they're only going to collide randomly, throughout, you can think like a billiards table or like a bunch of ping pong balls in like the lottery machine or something like that. If you decrease the temperature, that means you're going to have fewer collisions of these gas molecules. If you increase it, you'll have more. Excuse me. And then finally, pressure. Now, pressure isn't something that we have talked about much yet, but pressure is a measure of the gas particle collisions with the sides of its container. So you are probably familiar with the concept of pressure, whether it's from, let's say you drive a car or a bike. You know that you need to have your tire filled to a certain pressure of air. And as you increase the number of particles of air that you put inside your tire, that increases the number of collisions that are occurring with the outside of the tire. And that's what gives the tire the shape. I'm looking at my car right now and I need to fill the front tires. So you get the idea. Now, there's several different ways to measure pressure, There's millimeters of mercury, or torr. Those are nominally equivalent. There are atmospheres, and then there are pascals or kilopascals, and then finally pounds per square inch. We'll talk about more of these in a minute. Actually, did I put this in here? Here we go. Okay, so 760 millimeters of mercury equals 1 atmosphere of pressure. And that is what we need to note. Okay, so this right here is a barometer. You may be familiar with barometers from, I guess the first place I probably heard about a barometer or the measurement of pressure or the measurement of atmospheric pressure is from like meteorology reports on TV. Based on whether the pressure is rising or falling, meteorologists can predict whether or not there's good weather coming, bad weather coming, rain, all of these things. And the way a barometer works is that if you take a tube and invert it and fill it with mercury and invert it into a pool of mercury, this is all the liquid metal mercury, at exactly 1 atmosphere, which is approximately sea level, so pretty close to where we are here on the coast, the mercury in the tube will always be 760 millimeters above the mercury in the pool. So this gives us a measurement here of 760 millimeters of mercury. We have a big story to tell about the barometer in the future, but I just wanted to explain that to you now and also show you the conversion factor that 760 millimeters of mercury equals 1 atmosphere. and that also equals 760 torr. Okay, now our understanding of gases adds up to this, what we call the kinetic theory of gases. So this is like our modern understanding of the way that gases behave. A gas consists of small particles that move randomly with high velocities. They have no attractive or repulsive forces towards each other. In other words, they just bounce off of each other rather than sticking to each other or repelling each other. Again, you can think of these gas molecules like ping pong balls. They just bounce off each other from one way to another. They have a very small volume compared to the volume of the containers they occupy, as in the atoms themselves take up a very small amount of space compared to the overall space of the container. Therefore, a gas is mostly empty space. They are in constant motion. And finally, they have kinetic energies that increase with an increase in temperature. This is our modern understanding of gases. But what did we used to think that gases were? Like, we didn't know about molecules and atoms for forever, right? Until the 1800s, you'd say, that we had a solid atomic theory that we could understand. Well, you know, prior to the scientific revolution in Europe in particular, there was a type of philosophy called Aristotelian philosophy that was the favorite in Europe. And I want to say we're going to talk a lot about European history. So just kind of note that, you know, we see a lot of Europeans in this history, but it's not the only type of scientific history that there is. It just is these are the first people who discovered these properties. Nothing particularly special about Europe other than, in particular, this is where like really nice glass was developed first. And so I think they kind of got a head start on that, in addition to, you know, having a trading empire and colonial empires that were able to take labor and ore from all around the world and kind of add it up into, you know, into a system that produced scientists. But we'll talk more about the scientists and less about the imperial conditions. But of course, that's also an interesting, you know, consequence of history. Regardless, going back to Aristotle here, Aristotelian ideas were held in favor in Europe. And Aristotle basically, you know, these kind of controlled the foundation of cosmology. You look here and you see, okay, it's the Earth is surrounded by the air, and then there's fire, which is the sun, and then the moon, Mercury, Venus, the sun, Mars, Jupiter, Saturn, etc., move in perfect circles around the Earth, which is again the geocentric hypothesis or the geocentric idea of the solar system, where the Earth is in the middle. There were Aristotelian ideas in biology. So the idea was there's 4 humors in your system: blood, phlegm, bile, and one more that I can't remember off the top of my head. But the idea is, you know, if you need more of one, this is where the idea of bleeding comes from. Basically, it's like, oh, this disease means you have bad blood or you have too much blood, so we have to take blood out of you with leeches or, you know, just by draining blood. It didn't work very well. And then finally, physics, which is, you know, where we're going to start talking about today. For example, the idea of impetus over momentum. So momentum, we know, is you know, mass times volume. It's this idea that an object in motion tends to stay in motion, and an object at rest tends to stay at rest. You know, that's inertia. That wasn't the case with Aristotelian physics. They believed in impetus, where you provide an impetus, and then that impetus is depleted from the substance. Yeah, anyways, these are the old ideas, pre-scientific revolution. And one of them was this idea that you probably have heard of today, that nature abhors a vacuum. Here's this Far Side comic kind of showing the same thing. And the idea is basically that Aristotle proposed that vacuums were impossible, that if there were a vacuum in the universe, everything around it would rush in to fill it up. So a vacuum, therefore, would be impossible. Well, you know, when you hear these ideas and you think, oh, okay, I guess that makes sense, you should always think like, well, how would I prove it, right? How would I design an experiment to prove that wrong? And in enters Torricelli. So we have a picture here of Torricelli with his famous barometer. He was a student of Galileo, among many others, and he was the first to develop the mercury barometer that we talked about before. Basically, it's just exactly the same thing I was showing you on the previous slide. You fill a glass tube with mercury, you have a pool of mercury at the bottom, invert the tube into the pool of mercury, and always, no matter the size of the tube or whatever, this glass tube is always going to be filled with 760 millimeters of mercury above the pool of mercury here. Now, Aristotelian physicists at the time were thinking of ways that that this was not the case, because, okay, so what this implies is that a vacuum forms here in the headspace of this tube, because this was full of mercury before, and you didn't see any bubbles rise through mercury. That doesn't happen. And so you just see here this empty space. So Aristotelian physicists had all sorts of arguments against it, saying, this isn't a vacuum here. There's actually going to be glass particles that are coming off and just are generated from the space. And that's what we have here. There's also saying, this idea that this vacuum is holding up the mercury column. That's another thing that physicists would say at the time. Well, Torricelli actually designed a few experiments to help out with that. Note here the different sizes of columns that you can see, and the different shapes of the glass tubes. Again, a big part of the story is just the fact that in the 1600s in Italy, there was like a really good set of glass making processes. So you can imagine this happening anywhere in the world that had access to mercury glass. Just happened to be that Italy was the first to have those available. So Torricelli demonstrated that the height of the mercury was going to be the same regardless of the size and shape of the tube used. So his explanation was, rather than the vacuum holding this mercury up, instead it has to be the pressure from the atmosphere pushing the mercury up into the tube. So that's kind of the first explanation, implying that gases have some kind of pressure. And so the idea is, again, back here, atmospheric pressure, these are the particles of gas hitting that pool of mercury. And because they're striking that pool of mercury, they're pushing the mercury up into the tube. Okay, so this inspired a lot of other chemists and physicists around Europe, really, where this was being talked about. In the 1660s, Robert Boyle started working with these gases, and he noticed that there was a relationship between the pressure of the atmosphere and the height of the column, because he recently had worked on a separate development called the vacuum pump. And this is a very similar crude device here to what this is. You see there's a bell jar here, and this pump, which works almost exactly the same as the way that you pump up a basketball or a soccer ball, just in reverse, is designed to pump air out of here and get to a vacuum here. So here's a kind of a GIF mock-up of what that looks like. So this is the barometer here. Oh, sorry. This is the barometer here inside a vacuum pump. Vacuum is applied, and as you can see, as the air particles in the bell jar come out, the column of mercury actually decreases down until in their full vacuum, it remains level again. So again, this is really good evidence that the mercury in the tube is there because of the pressure of the atmosphere. Again, the atmosphere is pushing down the mercury, and that's what's keeping it full in the vacuum pump. This was experiment number 17 that Robert Boyle did. And again, he just did almost exactly this experiment by having a barometer in the vacuum. And we see that there. Now, not all of these experiments were so nice. Here's experiment number 41, which, as you can see here, this is a bird. So, at the time, it was a different time. And, at the time, just like a circus would go around and you just see, oh, hey, it's an elephant. Oh, hey, there's something at the circus. Chemists would go around and perform experiments like this. And this is one of the most dramatic ones here, because just in the same way that the vacuum pump takes air out of the bell jar, it can also take it out of your lungs in a very violent way if you're exposed to vacuum, like in space, for example. It was really dramatic when it was performed on birds. And sure enough, Robert Boyle did perform it on birds. Now, this experiment on a bird in an air pump, it's unclear how many times this actually occurred. Again, experiment 41 for Robert Boyle, he definitely did it. It seems like from historical documents, most of the other scientists who would go around doing this were actually, they were actually going to use, rather than birds, they would use like little rubber mock-ups of that contained air. And they'd say, oh, imagine if it's a bird. So it doesn't seem like everyone's quite as convinced that it's really interesting. Now you can see some other interesting experiments here on the table. This is a great painting. I totally forgot the name of the artist here. I have to put that on here next time I go through this slide. But you can see some other interesting experiments here, including there's a voltage generator. So that's the famous Volta experiment where he would apply a voltage to frog legs and make them hop even after they were dead. So that's kind of showing off here the experiments back in the day. Okay, all right. So now, after all of that, you have to remember that the Aristotelian philosophy had like a 1500 year or maybe 1800 year history in Europe. And so very influential philosophers, what we call natural philosophers today, were definitely against this idea. And they had, very strong arguments that they were trying to make against this idea of a vacuum that can form, and this idea of gas pressure, which wouldn't follow from Aristotelian thought. So Robert Boyle continued to work on this here. And again, the technology of glassware figures in heavily to this history. In England, they were able to develop what's called a J-tube or a U-tube. And this U-tube basically allows you to trap gas on one side. And what you can do is if you fill mercury up here to where it's level on both sides here, and you trap a certain volume of gas in here, if you double the column of mercury here, what you notice is the volume that the gas is occupying actually decreases by half. So by doubling the pressure, you increase the volume of the gas, or I'm sorry, you decrease the volume of the gas by half. And this showed that there was a relationship between the pressure exerted on a gas and then the volume of the gas, which brings us to Boyle's law. So this is why Boyle gets the credit for this name, is this experiment here. Some experiment should go to his assistant, Robert Hooke, who, a brilliant experimental chemist, physicist, scientist in his own right in England and the Royal Society. Anyways, that brings us to Boyle's law. And, stated succinctly, it says, the volume of a fixed quantity of gas is inversely proportional to the pressure exerted by the gas at constant mass and temperature. So keeping the same amount of gas at the same temperature, if you double the pressure, you have the volume. The way that we most commonly write this is that the initial pressure times the initial volume is equal to the final pressure times the final volume. So that's how you can kind of figure this out. P1 V1 equals P2 V2. And that's what we're going to do here as we move into the sample exercises. So this says sample exercise 2. I think I forgot to include here a sample exercise on conversion factors. Just know that you need to be able to convert pressures from atmosphere to millimeters of mercury and torr, just be able to convert between those three units in particular. And we may talk about pascals at a later time. But for now, let's go ahead and try to do some of these pressure volume relationships. So here we go. A sample of oxygen gas has a volume of 12.0 liters at 600 millimeters of mercury. What is the new pressure when the volume changes to 36.0 liters at constant temperature and amount? N stands for moles, but it can also be grams. Okay, well, so when we do this type of problem, we want to recognize what's P1, what's V1, and then what's P2 and what's V2. So looking here at 12.0 liters and 600 millimeters of mercury, that's what it starts at, right? So that tells us that V1 is 12.0 liters and P1 is 600 millimeters of mercury. And then it's asking what's the new pressure? Well, that would be P2, sorry. when the volume changes to 36.0 liters. That's V2. So what are we solving for here? Well, we're looking for P2, right? So let's just go ahead and apply that P1V1 equals P2V2. Sorry. Here we go. So if we solve for P2, we would find that P1 times V1 divided by V2 should equal P2. Then all we have to do is plug in our numbers. We started with P1 of 600 millimeters of mercury. We have V1, 12.0 liters, divided by 36.0 liters. Multiply it all out, you end up with 200 millimeters of mercury. And I think it should be 3 significant. Well, I guess, yeah, it doesn't really matter the significant figures for this one in particular. Okay, so here we go. Sample exercise 3. For a cylinder that contains helium gas, indicate whether cylinder A or B represents the new volume for the following changes, noting that the amount and temperature are again constant, for reasons that we'll find out in a bit. So step 1, if pressure decreases, which one is likely to be occurring? Keep in mind, if the pressure of the gas is down here, is it going to take up more volume or less volume? That's this idea of this piston system. And then finally, if the pressure increases. Okay, well, if the pressure increases, that means that the volume has to decrease. So that would represent cylinder A here, where because the pressure increased, the volume decreased. And then finally, if the pressure decreases, that means the volume is going to increase, just like the volume here in cylinder B is greater than what we started with. Okay, finally, sample exercise number 4. If a sample of helium gas has a volume of 120 milliliters and a pressure of 850 millimeters of mercury, what is the new volume if the pressure is changed to 425 millimeters of mercury at a constant temperature and amount? Go ahead, pause the video here, work it out, and then when you come back, we'll take a look at the answer. So go ahead, pause. Okay, so we're back. It says that we have a sample of helium gas at a volume 120 milliliters, that's V1. Pressure 850 millimeters of mercury, that's P1. And then what is the new volume if the pressure changes to 425 millimeters of mercury? That's P2, and we're looking for V2. So that means we just need to use Boyle's law. V2 would equal V1 times P1 divided by P2. So that's 120 milliliters times 850 millimeters of mercury divided by 425 millimeters of mercury. The answer should be 240 milliliters. Note, one thing that's really good about these laws is that whatever unit you're using here for pressure and volume, the only thing that matters is that the units for pressure and volume match in the final. So if you start with liters, liters in atmospheres, that's great. Or if you have millimeters of mercury in milliliters, that's fine too. But P2 and V2 then have to match those units that you start with. Oh, shoot, I forgot. There's another one. A sample of helium gas in a balloon has a volume of 6.4 liters at a pressure of 0.70 atmospheres. At 1.40 atmospheres is the new volume represented by A, B, or C. Go ahead, pause the video, think it through, and let's take a look at the answer. Okay, so what happened here? We went from 0.70 atmospheres to 1.40 atmospheres. That means we increased the pressure on the balloon. Now, what happens when we increase the pressure? What happens to the volume? The volume decreases. Therefore, when the volume decreases, it's going to be a smaller balloon. So that would measure balloon A. Okay. Okay, so that's Boyle's law. Now let's talk about the relationship between pressure and temperature and volume and temperature. Now, the key development for this is that the thing we have to remember is that temperature itself has been very difficult to measure for a long time. So before the relationship between the pressure and temperature or volume and temperature of a gas could be measured, a temperature scale had to be developed that was pretty consistent. Enter Frenchman Guillaume Amanton. He was working on a totally different problem, a thermal engine, basically that could, use heat to generate motion. And he noticed that when he took a gas from an ice cold temperature to a boiling hot temperature, and he kept it at a constant volume, the pressure that was exerted by the gas increased by about a third. So going from about 0 degrees Celsius to 100 degrees Celsius, the volume, the pressure, exerted by that gas increased by a third. This was part of the original idea behind thermometers. So basically the idea is here, you can develop a thermoscope where you can measure relative temperatures based on the pressure exerted by this gas. So if the pressure, or sorry, I think it's by this gas here. The pressure exerted by this gas increases, that's going to push the liquid in the tube up. So you'd see a relative increase in temperature. Now, that's not really good because you don't have like a scale. So it took the development of a mercury thermometer by our friend Fahrenheit in 1714 to be able to reliably measure temperatures. And once those temperature measurements became reliable, all of a sudden, now we were actually able to do the important experiments that we could. The first person to get credit for the relationship between volume and temperature is Jacques Charles, another Frenchman. He's seen here setting a height record for ballooning. He heated 5 different gases to the same degree and recorded that each gas increased in volume by the same amount. Now, he never actually published these findings. He only really talked about it to his friends. But as it turns out, he had some really good friends. His friend, Joseph-Louis Gay-Lussac, redid those experiments with greater precision, and he published all of them. But to his eternal credit, he actually gave Charles he gave Charles full credit for discovering this relationship between volume and temperature for gases. Now, why would that be? Well, they were good friends, and in fact, they were balloonists together. So you can kind of imagine, when you're on a balloon with a person, going up to, in this case, 4,000 meters, which at the time was a record height, you get to know someone pretty well, right? So Joseph, was a really good friend to Jacques, and gave all the credit for this relationship between volume and temperature to Jacques Charles. So what else did I want to say here? Yeah, really interesting story here. Jacques Charles and Gay-Lussac, Joseph-Louis Gay-Lussac, were both balloonists here. That's why they were interested in gases. At the time, they were, looking at unpowered flight and how high could they get. And so they would fill these balloons with hydrogen and see, how high up could they go. And everyone was racing to get to the highest. What did I want to say here? Okay, here. So once we developed an absolute temperature scale, which is credited to William Thomson, we came up with this scale here. So now here you'll notice I just said, he noticed that, when he heated it up, the volume increased by the same amount. That's because at the time they didn't have an absolute temperature scale. So it took the development of Lord Kelvin's temperature scale, absolute temperature scale, for us to be able to understand exactly the relationship. And the relationship is this: the volume of a fixed quantity of gas is directly proportional to the absolute temperature of the gas at constant pressure. In other words, the volume divided by temperature relationship for a given gas at a constant pressure is constant. Or the way we write it more often is that the initial volume divided by the initial temperature of a gas is equal to the final volume divided by the final temperature of the gas. Okay, so that brings us back to our sample exercises here. Sample exercise number 6. A sample of oxygen gas has a volume of 420 milliliters at a temperature of 18 degrees Celsius. At what temperature degrees Celsius will the volume of oxygen be 640 milliliters? Given that the pressure and amount are constant. Well, for this one, we note that we have a relationship between temperature and volume. So this should tell us that, we need to use Charles's law. And Charles's law, again, V1 over T1 equals V2 over T2. Now, what I forgot to mention in this last slide is that the temperature for this equation has to be in Kelvin. You cannot use Celsius, you cannot use Fahrenheit. You have to have the temperature in Kelvin. So the first thing that you need to do always is convert your temperatures to Kelvin. So 18 degrees Celsius, that becomes 291 Kelvin, and that is our initial temperature, T1. Now T2 is going to equal T1 times V2 over V1. And when we solve for that now, using our V2 of 640 milliliters, our V1 of 420 milliliters. That gives us our answer of 443 Kelvin. Now, if you're asked for the temperature in degrees Celsius, then you could, just simply subtract 273.15 again, and you get your 170 degrees Celsius. Okay, so here's our thought exercises. Why don't you go ahead, pause the video here, and complete the sentence with either increase or decrease, depending on which is the correct relationship between the two statements. So A, for example, says pressure blanks when V decreases at constant temperature in moles. Tell me, is it increase or decrease? So go ahead, pause the video. Okay, let's go ahead and take a look. So pressure increases when volume decreases at constant temperature in moles. When temperature increases, volume decreases at constant, when temperature decreases, volume decreases at constant temperature in moles. Pressure decreases when volume changes from 12 liters to 24 liters, and then finally, volume increases when temperature changes from 15 to 45 degrees Celsius. Okay, now Gay-Lussac didn't stop there. In fact, he should get a lot of credit for what we're about to talk about, because he came up with, or he noticed that when he did research on the reactions of gases, he noticed that when gases combine in similar volumes, they would produce the products in whole number integer ratios. So in other words, like one volume of hydrogen reacted with 1 unit volume of chlorine, and it always produced it at constant pressure 2 unit volumes of hydrogen chloride. Now, this makes sense to us nowadays, but it didn't necessarily follow from what people had learned before. For example, the densities were all different. People didn't know about atoms and molecules at the time, so it wouldn't have made any sense. Enter our good friend Amedeo Avogadro. And based on the back of this work, he proposed that the volume of a gas was directly related to the number of molecules of a gas. This at the time was actually really controversial, but basically the idea is, again, if we're gonna, do I have it in the normal form here? Yeah, so it's in the normal form on the next one. But the basic idea here is that the volume of gas is going to increase as you increase the number of particles. And again, he just said, oh, it seems like this is the easiest way to explain it, is that equal numbers of molecules of gas occupy the same volume. And this makes a lot of sense. Now, think about like blowing up a balloon. As you blow up a balloon, you're increasing the number of molecules or moles of molecules in the balloon, and it's occupying a greater volume, even at the normal atmospheric pressure. So if you keep temperature and pressure constant by doubling or by increasing the number of moles, you're going to increase the volume. So if 1 mole gave you 1 liter at a certain pressure and temperature, then 2 moles would give you 2 liters at that same pressure and temperature. Okay, so again, this is the way that we're going to use it most often for Avogadro's law. V1 divided by N1 equals V2 divided by N2. And N here means the number of moles. Okay, so here we go. Let's do an example calculation. If 0.75 moles of helium gas occupies a volume of 1.5 liters, what volume in liters will 1.2 moles of helium occupy at the same temperature and pressure? Well, we have our relationship here. We have an amount of moles and we have a volume. And then we change the amount of moles. How does the volume change? Well, this is clearly an application of Avogadro's law. We have V1 here, N1 here, and then N2 here. So we must be looking for V2. So we set up our solution for V2, solve for V2. It should be equal to V1 times N2 divided by N1. Plug in the numbers that we have from our equation here. It's 1.5 liters times 1.2 moles divided by 0.75 moles. That's 2.4 liters. Okay, now at this point, it's important for us to understand what's called standard temperature and pressure. You can compare the volumes of gases at what we call STP, which is just our unit standard of temperature and pressure. Because of what we just said about Avogadro's law, gases that are at the same temperature and pressure are going to occupy the same volume if they have the same number of moles. So we define standard temperature as 0 degrees Celsius, or of course 273 Kelvin. And then standard pressure is defined as 1 atmosphere or 760 millimeters of mercury. Now, at standard temperature and pressure, the average gas is going to occupy about 22.4 liters. And this is what we call the molar volume. So this is now going to be a way for us to be able to convert between the volume of the gas and moles of the gas. 1 mole of a gas always occupies 22.4 liters at standard temperature and pressure, or you could say that 22.4 liters of a gas accounts for 1 mole of gas at standard temperature and pressure. Note, if it's not 0 degrees Celsius, or if it's not 1 atmosphere, this whole conversion factor does not apply. So you have to be looking for those particular units, or look for the phrase STP. So yeah, whether you have 1 mole of helium, 1 mole of oxygen, or 1 mole of nitrogen, they have different masses. You know, the mass of helium is 4.003 grams for 1 mole. It's 32 grams for oxygen and 28.02 grams for nitrogen. But each of them occupies the exact same volume, 22.4 liters. Okay, let's go ahead and do a sample calculation here with molar volume, which can help us understand what we're talking about. Let's say, what is the volume occupied by 2.75 moles of nitrogen gas at STP? Well, if we know the number of moles, then we know that we can use the molar volume to convert from the moles of gas to the volume of the gas. And that molar volume is 22.4 liters per 1 mole. So 2.75 moles of nitrogen times 22.4 liters per 1 mole. That gives us 61.6 liters of nitrogen. That's how we can use the molar volume as a conversion factor. Okay. Now, something that you might notice here is that all of these units seem to be related to each other. The pressure, the volume, the temperature, and the number of moles. Even when we were just comparing the pressure and the volume, we knew that we had to keep the amount of gas the same and the temperature of the gas the same, or it throws everything off. So it was just kind of waiting for someone to pluck this off. And sure enough, Benoit Clapeyron, who was a engineer at the time, trying to work out, a good steam engine, he determined that the pressure and volume divided by the temperature are always constant for a given gas. In other words, if we're putting this into a way that we've put things before, the combined gas law looks like this: P1 times V1 divided by T1 equals P2 times T2 divided by, sorry, hold on, get the eraser. So P2 times V2 divided by T2. And this is kind of an equivalent way of writing what we have up here. So yeah, everything's related. That means that we can combine these gas laws that we talked about into a single law, the combined gas law. And if you're not good at remembering the other ones, if you can remember this one, well, it accounts for every other relationship. For example, if temperature is constant, that means that P1 times V1 equals P2 times V2. That's Boyle's law. Okay, if pressure is constant, well, that's V1 over T1 equals V2 over T2. That's Charles's law. And then finally, if you know volume's constant, well, then P1 over T1 equals P2 over T2. That's Gay-Lussac's law. So all of these are ways that you can remember how the relationships work between pressure, volume, and temperature for a gas. Okay, let's go ahead and apply that. Now, these calculations tend to be a little arduous because you have 6 different things to keep a track of rather than 4 different things, but it's the same kind of math. So let's go ahead and walk through sample exercise 9 first. A sample of helium gas has a volume of 0.180 liters, a pressure of 0.800 atmospheres, and a temperature of 29 degrees Celsius. At what temperature, in degrees Celsius, will the helium have a volume of 90.0 milliliters and a pressure of 3.20 atmospheres? What do you notice about this right away? 2 things, right? What's the unit of temperature? Degrees Celsius. So in order for us to be able to use the combined gas law, we know that we need to convert that into Kelvin. So keep that in mind. We got to do that in Kelvin. Okay, what else? What are our pressure units? 0.800 atmospheres at the beginning, 3.20 atmospheres at the end. Okay, that's good. Now, how about volume? We started at 0.180 liters, and we ended at 90.0 milliliters. Wait a second. Those units don't match up. We need to make sure that our units are going to match up before we do this problem. So that's the number one thing. First off, convert the temperature to Kelvin. Not too bad, 302 Kelvin. Next up, make sure that you convert your volume units into the same unit. Okay, so starting from P1 times V1 over T1 equals P2 times V2 over T2, and you solve for T2. Now, this is a little annoying, but you can imagine multiply both sides of the equation by T2. Okay, that gives us T2 on this side. Then divide both sides of the equation by P1 times V1. So you get P2 times V2 over P1 times V1. And then finally multiply both sides of the equation by T1. So T1 over here. Okay, now 0.180 liters converts to 180 milliliters. So we can just simply now plug those volumes in along with the pressures and the temperatures. So it's 302 Kelvin times 3.20 atmospheres divided by 0.800 atmospheres times 90.0 milliliters divided by 180 milliliters. That gives us our 604 Kelvin as our answer, which converts to 331 Celsius. Okay, so next up, we have the ideal gas law. Now, the ideal gas law includes the combined gas law and the Avogadro's law. So by including the number of moles, now we can make up our ideal gas constant R and have this as our ideal gas equation, where the ideal gas constant is equal to the pressure times the volume of gas divided by the number of moles of that gas and the temperature of that gas, of course, in Kelvin. Again, this was really crucial for our understanding and the building of efficient steam engines, which again happened relatively shortly after the solution of this ideal gas constant in the late 1800s. So yeah, that brings us to our ideal gas law. And this is how it's usually written. P times V equals N times R times T. And R is our universal gas constant. Now, I thought I had the universal gas constant written here. There's a few ways that it can be, depending on the units that you're using. It can be 0.08206 liters times atmospheres divided by moles times Kelvin. And I guess that's a little confusing. Maybe can I? Nope, hold on. Here, let's change these X's out for asterisks. I think that's a little less confusing. So this is the one that we're most often used because our pressures are mostly going to be in atmospheres. Now, later on, we'll talk about our ideal gas constant in kilopascals or pascals, because that's also very useful for different reasons, but different calculations. Okay. Okay, now that brings us to the final gas law, which is the law of partial pressures, also known as Dalton's law. Dalton's back, that's right. So we have Avogadro back this chapter, we have Dalton back this chapter, all the heavy hitters are here. So Dalton was in correspondence with Gay-Lussac in particular about his atomic theory, and Avogadro as well, to try to understand, what particles of gas are made of. And he noticed that when you mix gases together, basically the pressure of each gas adds together to give a total pressure for the mixture of gases. So for example, if you took a sample of helium that was at 2.0 atmospheres at a given volume and added it to a sample of argon that was at 4.0 atmospheres at a given volume, you combine them together, you have 2.0 atmospheres from helium, 4.0 atmospheres from argon, and that adds up to 6.0 atmospheres. This is the law of partial pressures. And again, the partial pressure of a gas is the pressure that each gas in a mixture would exert if it were by itself in a container. And the law of partial pressures looks like this. Basically, the total pressure of a gas depends on the total number of gas particles, not the individual types of particles. And the total pressure exerted by gases in a mixture is the sum of the partial pressures of those gases. So like, for example, At STP, 1 mole of a pure gas in a volume of 22.4 liters exerts the exact same pressure as 0.4 moles of oxygen plus 0.6 moles of helium, or 0.5 moles of oxygen plus 0.3 moles of helium plus 0.2 moles of argon. No matter what, this total sum here is going to add up to 1 atmosphere. Air, for example, is a mixture of different gases, mostly nitrogen and oxygen. It's 78.2% nitrogen, 21% oxygen. Then there's a big component of carbon dioxide, argon, and water vapor that will vary depending on things like the humidity, how close you are to, let's say, a very forested area, or you are to industrial pollution, all of that. So the atmospheric pressure that we feel is actually the sum of all the partial pressures of these gas particles in the air, the nitrogen, oxygen, and others. Okay, so what type of math do we have to do for partial pressure? Well, if a scuba tank contains oxygen with a pressure of 0.450 atmospheres and helium at 155 millimeters of mercury, what is the total pressure in millimeters of mercury in the tank? Keep in mind here, volume and temperature are constant. Well, how do we solve for this partial pressure? We know that the total pressure is going to equal the partial pressure of the oxygen plus the partial pressure of the helium. So we simply need to add them together. Now, here's a big problem. Our units are different. We have atmospheres for oxygen and millimeters of mercury for helium. So we need to first convert the atmospheres to millimeters of mercury. So we use our conversion factor. There's 760 millimeters of mercury for every 1 atmosphere. That gives us 342 millimeters of mercury for oxygen. Now we plug in 342 millimeters of mercury plus 855 millimeters of mercury for the helium. That gives us a total pressure of 1.20 times 10 to the 3rd millimeters of mercury. Okay, now we're ready for sample exercise 11. A lot of these are about scuba tanks because scuba tanks are one of the most important applied instances of partial pressure, so we talk about it a lot. Okay, for a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8.00 atmospheres. If the oxygen has a partial pressure of 1,280 millimeters of mercury, what is the partial pressure of the helium? Volume and temperature are constant. So go ahead, pause the video here. See if you can figure out what the partial pressure of the helium is. And once we unpause the video, we will walk it through, and I will see you in a minute. So I'd pause. Okay, let's walk it through. So what do we know? We know that the total pressure is 8.00 atmospheres. We also know that the total pressure is a sum of the partial pressure of the oxygen plus the partial pressure of the helium. And finally, we're given the partial pressure of the oxygen, which is 1,280 millimeters of mercury. So all we have to do is convert our units from atmospheres to millimeters of mercury, or millimeters of mercury to atmospheres, and solve for the partial pressure of helium. So let's take that total pressure, 8.00 atmospheres, convert it to millimeters of mercury using our conversion factor. There's 760 millimeters of mercury for every 1 atmosphere. That gives us 6,080 millimeters of mercury. Okay. The partial pressure of helium then is 6,080 millimeters of mercury minus 1,280 millimeters of mercury for a total of 4,800 millimeters of mercury. Okay, and that does it for the gas laws. So I hope that was fun. Let me know if you have any questions in the comments below. And until then, I will see you soon. Bye-bye.